to do so. Okay, so we're going to continue on talking about this issue of functional abstraction that we talked about last time. When we say functional abstraction, can anyone unpack that? What do I mean by functional abstraction?
Breaking down large chunks of code into smaller pieces of code represented by functions.
Great. Excellent. Your name?
Eric.
Eric, yes. So, as Eric said, functional abstraction provides a mechanism for achieving modularity by breaking a larger system up into pieces, where the pieces are captured by functions. And we saw that some last time with the code. It wasn't this code. That's another ball of wax. In going from this code, maybe we could, I'm just thinking, I was in a class on Tuesday. I was sitting in the back, and this was really faded. Now your eyes are younger than mine, and you may have better vision. But let me just try going to the back here. Is that a bit better? Okay. The code was bad enough. To have to squint at it is horrible, right? It was already inscrutable enough. Okay, so there's some code that I provided you, and we talked about how to improve it. And I showed you, and then I provided on the website for further building, one way of sort of breaking this code up into functions. Now this way lacks some features that we're going to be introducing, but fundamentally it took this larger program and it broke it up into a bunch of functions, right? So we had a function to run the scenario, to update the space, to update the cell, to compute liveness of a cell, count the surrounding, count the number of live cells around a cell, etc. And each of those, per best practices in companies that are over at the career fair today, these are broken up into small chunks. Each of the chunks has a job in life, and each of the chunks has clearly defined dependencies in the form of parameters, of formal parameters or arguments, and returns values. It may modify other things, but it's a lot clearer what it depends on and what it does, if only because it has the name. And in going from this to this, a lot of things become considerably clearer. And the name helps. The fact that we don't have to look at all code at once, the fact that we can just look at the high-level structure up here, that we read the state, we run the scenario, we write the state. That tells us a lot about, at a high level, what's going on, in a way that staring at this large block of code does not. We have to kind of wade through a bunch here to get the clarity that basically this is what's happening. We read the state, we do some computations, and we write the state. And the same thing with running the scenario, the fact that we're going over time, etc. So naming helped that. But we did something else besides that, ladies and gentlemen. In creating these functions, we used a technique that's known as abstraction by parameterization. And what I mean by that is, instead of depending on this hard-coded value that we perform this loop for 100,000, and you may have to try to figure it out the first time, but 100,000 steps. We're doing this 100,000 times. That's hard-coded here, right? And this is hard-coded, 100, just down there for the, remember what this denoted? This was the what?
Each of the rows and columns.
Yeah, the number of rows and the number of columns, right? A and B don't really tell you the rows versus columns. And we talked about how naming matters a lot and should really be improved. But the point is, this stuff is hard-coded right now. And Royce earlier had said, look, all these magic numbers, are real problems, and they are. They're huge problems. If you go to change something, you may forget. You want to change 100 to 1,000, you forgot to change 99 to 999, right? And then there's the question, is this 99 because of this 100 or because of that 100? And all those things are hidden. We talked about how those can be improved. But the fact remains that this code was very specialized. It had almost no generality to it, in the sense that it was written very specifically and assumed a space of a certain size and a certain length of computation. And one of the things that you did, probably many of you, and that certainly I did here, was to abstract that. In other words, when I went and coded these things up, for example, saying update the space here, run a scenario, I had it provided a number of steps. How many steps? For how many steps should it run? Right? That's going from that very hardwired, concrete 100,000 steps to a situation where it's parameterized. So now we could reuse this run scenario with different numbers of steps, right? We could say run it 100 times, we could say run it 100,000 times, and it would run. Very modest in its gains here, but very significant. We've gone from a hard-coded situation, a hardwired situation, to one where we have some extra flexibility. And although this is modest, although it's just a small step forward, you will find that doing that writ live, or writ large across the entire program, can be very helpful for sort of generalizing things. And so there's quite a few places, for example, in this read state or in this write state, where we achieved generality as well by abstracting away from the file name. Before, in the code earlier, the code from what we saw here, those things were hard-coded, right? Now we have code that could work with multiple names. Maybe the user could specify as a command line argument the name of the file to read, and it would do that, right? More than that, though, ladies and gentlemen, we can go and abstract away from additional features. For example, this determine and current and next cells, where we sort of say, okay, which is the next column to use, allows us, or the next array to use. This allows us to use the same update cell method or function here. And this same update cell method basically replaces two chunks of code in this original code. Can anyone point out what chunks of code did that update cell allow us to sort of to simultaneously deal with one chunk and another chunk? What were the two chunks? I'll go back to it just so you could see it. Here's update cell here, and here's the code for it. We count the number of surrounding live cells. We get the index for the current cell. We determine if it's alive, and then compute liveness for that cell, depending on whether it's alive and the number of cells around it that are surrounding. This code, what code does that subsume? What code does that kind of get rid of here? Yeah, the two blocks of ifs, right? Why two? Why do I emphasize two here?
The two blocks are duplicated.
They're basically, conceptually, they're the same thing. They only differ in one.
Which arrays they're using.
Which arrays are being used for the input and the output, right? This top one uses reads from B, the current state, and updates A, and the bottom one does reverse. That's all there is that's different. And we've abstracted that. We've abstracted that difference. We've created something more general with update cell here. We've abstracted out. We provide as a parameter information on which are the current ones and which are the next ones. So in short, the naming was different, but in one case we could call it with basically the current cells are in B and the update is to A, and then vice versa. And it will allow us to do in one place, in one piece of code, a lot clearer code too, one piece of code, it'll allow us to do things that used to be splayed out into multiple pieces of code here. Multiple pieces that could each have the same bug and each have to be fixed in turn, and pieces that are unnecessarily large and confusing. So, in short, and this is really important, we had this notion of introducing so abstraction. So this is functional abstraction is what we're talking about. Functional abstraction, introducing these functions that abstract, and we introduce specifically abstraction by parameterization here. By parameterization, what I mean is that we introduced parameters that allowed a single piece of code to handle multiple situations. Right? This single piece of code, this what used to be 2 blocks of code, because we introduced parameters, can now be handled in a single block. You see that? And similarly, what would have had to be multiple blocks of code to run a scenario with different numbers of steps. In other words, we would have just, if we wanted to run this with 1,000 steps instead, we could have copied this whole block and copy and pasted it and made it 1,000. Now we've captured both of those, the ability to do either one with it. Just provide the common steps you want to do and it will do the job. So we've abstracted, we've made something that's more general, hiding the details, the vagaries of how many steps you're going to do it. We've made it more general by introducing a parameter, okay? That was last time, but it's a very important notion. And it's going to carry us through the semester in different forms. We're going to see how that plays a role in the context of type parameterization, where you take a linked list and you parameterize it by the type of element in that linked list. You go from a linked list of doubles and a linked list of hash tables and a linked list of strings to a linked list, and you can provide whether it's an indication whether it's a string or doubles or hash tables or whatever. Okay? Abstraction by parameterization. You see it here in this code, although I didn't highly emphasize it last time. But basically, we've simultaneously made this code smaller, cleaner by abstracting with parameters. Okay? Now, today, I'm emphasizing this because today we're going to be emphasizing a different component. We're going to be talking about another component of abstraction, another way to achieve abstraction that you don't really see strongly represented in this code now, but which for next class, based on the code I posted, you will be undertaking an assignment, a take-home exercise. And this is abstraction by specification. Okay? The idea here is that we're going to achieve generality of the code. We're going to achieve ability to reuse it by hiding the details of exactly what algorithm, exactly what data structures are used inside this code. And we're just going to describe with comments, in case of C, sort of what this does. And that will allow generality because it allows any number of different particular implementations of this, like whether it's using a bit vector or not, to all be captured in an interchangeable way. You could just plug it in and you're done. And that's part of modularity, right? We talk about a car being modular if you can take out a piece of it, put in a new one, and the car runs just as well or runs better than it did earlier. All we've done is improve the performance, and we don't have to tinker with everything else in the car. It's modular. We can replace pieces of it easily. And that's what abstraction by specification will give us. It will allow us to take many particular ways of writing update space and be able to treat them as more or less interchangeable from the point of view of the person who's using them, such as in run scenario. Okay? So, abstraction by specification is what we're going to be emphasizing today. Abstraction by parameterization is something that we talked about last time just a bit, but I want to emphasize today. Any question about this notion of abstraction by parameterization? Again, the notion is we can go from something that's hard-coded and specific to something that handles a lot more cases by capturing things with parameters. We use the parameters to tailor the situation to a particular context. We reuse it by just using different parameters in different cases. And therefore, we don't have to rewrite it or have a complete copy of it. Make sense? Okay. Okay, so I posted some slides on that as well. And excuse me, I've got to be careful. I produced some slides for posting. I'm not actually sure I posted them. If not, I'll do it right after class. So I may stand corrected in that. Okay. So that's one thing I wanted to emphasize that was a theme for last time. I also wanted, though, to emphasize another thing that some of you will remember from 214. And that has to do with this role of what I call side effects. This is very relevant to our next couple lectures. And it has to do with things that make programming challenging, particularly programming with procedural, imperative, and object-oriented languages. Okay? So a side effect here is a term that's used to refer to an observable change to program state. Okay. Sounds really fancy. Okay, what do I mean by program state? I mean the current situation in the program. So a side effect might be something that changes an array, right? Changes a global array, changes a data structure. Maybe a side effect is something that changes the state of a database. Maybe it's something that updates something on the screen. Something has been changed in the current situation in the program because of a side effect. Now you may say, well, wait a minute, I mean everything's a side effect. It's not quite true. Not quite true. Could you give me an example of a piece of code that doesn't, so you call off to it, it does something meaningful, but it doesn't perform a side effect in the sense that it performs an observable change to things. No persistent observable change occurs. Can anyone give me a function that would be useful?
Wait, sleep.
Yeah, okay. You could ask it to sleep. Yeah, although you could say, okay. Yeah, it depends on sort of your how broad your scope is in terms of saying, okay, is the state of the whole machine changed or the state of that process changed? Because for now it's sleeping for a while. But if you're just thinking that, okay, you call it, and then essentially it wakes up after you're done, after that amount of time, you could say, well, nothing happened during that time from the point of view of this particular process or thread. Okay, how about another one? What would be a useful function that performs no side effect? Okay, suppose you have a number and you want to compute its square root, right? Call off, it gives you back its square root. There's been no side effect of that in the sense that it didn't leave any persistent mark. You got back a number, but it didn't change the state of the whole system, right? You could call it twice, and it'll give the same result every time. It's not like it's changed something, so it's going to give a different value. It's not like it's remembered that it was called earlier. In short, it's functional, meaning you call off to it, and it returns a value, and nothing persistent has changed. You get back this value, but it hasn't gone and updated the graphics on the screen. It hasn't gone and sent a message off over the Ethernet. It hasn't gone and put something in the database. It hasn't posted to some website. All it's done is compute this thing and give it back to you. There's no persistent observable effect. All it did is compute a value for you. Does that make sense? Do you grok that? And there's, in fact, lots of functions where this occurs, where basically what we want it to do is, we'll sometimes call them queries. We make a request, it gives us back some information, but it doesn't change anything. Now, there's another type of function which does something. And programmers in industry will often distinguish between these two types by giving them different names. So one name, it might be perform this, do this. If you go look at the APIs out there, you'll find different naming conventions, but they basically give names for things that have side effects that are different for those that just return a value. Get, right? Get X, for example. Compute this, which would be side effect free. They just return a value. How many people here remind me of Take It 340?
Take it now.
Take it now. Okay. What language are you starting with?
Pascal.
Okay, good. So Haskell is an example, and it will dovetail well with some of these points I'm making. Haskell is an example of a language that's a functional language. You can do incredibly powerful things. In fact, anything you can do in C, you can do in Haskell. They're both computationally universal. Anything you could do with a Turing machine, you can do in either one, given enough memory. But in Haskell, it's a particularly nice example language for sort of demonstrating certain features, particularly functional systems. So you can create a function that returns a value, and that value could be a reference to a function. Or it could be a number, it could be a string, or what have you. So Haskell is going to be filled with these sort of side effect-free functions. Now, why do we care about this? I mean, this may seem like an arbitrary definition. Well, it's not. It's not. It matters. It matters to you late at night when you're trying to figure something out with code. It matters when you're trying to get something correct for your program. Why? Because the presence of these side effects, these modifications, can really complicate our reasoning about a program. Okay, and the deal is that basically, if you look at a set of code, often one of the big reasons it's confusing is because you're not sure what depends on what. What things are modified earlier you need to have this code working. So you're not clear about on what values it depends, what it changes, what it computes. You know, you're not sure what this code does. That's how we say it, right? So let's go back and look at our anti-pattern here, right? Our anti-pattern in the form of, okay, now it's over in Linux land, so give me a second here. Okay, so where's my, come on, I just want to get, here we go. Okay, I know you probably didn't want to see this again, but it's gonna haunt us. Okay. So here's code. One of the reasons this code is a little bit confusing is because it's not clear what depends on what. You know, like where, for example, this C value, where was that computed previously? And you know, this, for example, these are counting up C's. Where was it modified? So this C, where did it come from? We'll sometimes say, well, it was modified here, and potentially all the way up here, and oh, this is where it was initialized. You know, so when you're trying to understand code like this, one of the reasons it's challenging is because you're not sure when you first glance at it, like, did C come from the previous iteration? Like, could it have come from, 10 loops ago? Or was it just only modified within this loop? So a lot of what's challenging here is seeing what depends on what. And some of you may remember a discussion of this in the context of 214, where I emphasized some of these characteristics. So let's go take a look at this. So I think this is the example actually I showed to you, to many of you back then. So here we have a simple computation going on, and there's a couple variables. And what's not clear is sort of where these variables come from. So here we have, for example, a computation that takes place in chunks where we're doing some things in a row here. And if you go and you look, like this uses total revenue, and even though it's nicely named, you kind of got to look up and see where did it come from. And then before this, where did that guy come from? Similarly, this revenue fraction for city, you have to see, okay, where did that come from? Where was it created? Count cities. Oh, okay, that's the same one as this one. This array revenue for city, it's the same one. So part of what's going on when you look at code is that the dependencies are not clear. Okay? What depends on what? What's the same thing as what? And this is why it can take time to kind of go into code and understand, okay, what's happening there. Now, the reason this is relevant to functional abstraction is because we can really reduce this this overhead. Okay, so here's another piece of code. Okay, we're taking a dot product. We're taking magnitude square, and where is that coming from? Well, we're we're taking the magnitude squared of this variable I, this vector I. Here we're taking vector, the dot product of the vector times with the dot product with another vector. And then here we're using both. We're using this dot product, and we're using the square root of the magnitude. Okay? There's a lot going on here, a lot to look at. Now let's see how this can be simplified through functional abstraction, right? We have these pieces, all these computations are going on, and secretly, if you trace through, they depend on each other, right? This normalized x depends on this thing, which is allocated. This magnitude depends on this, which itself is the square root of this guy, which is first initialized up here. There's a lot going on here in terms of how it's not that each line of code is terribly complex. It's how does it interact with, how is it entangled with earlier lines of code? Do you understand that? So when we go to try to understand code that's given to you, a lot of what's going on in your head is trying to figure out what depends on these things when it's written in this sort of way. Let's see how it could be simplified through functional abstraction, okay? Let's see how code like this, which is written out in this way that's eventually understandable. I mean, the names aren't terrible, so you can eventually understand what's going on, but it's just needlessly complicated. How can it be simplified through functional abstraction? Let's take a look. Okay, so let's take a look at these two examples. So here was this earlier one we looked at, and we're going to go and rewrite it in a functional style, this bottom one here. So here, what we've done is taken the same code functionally, and we've used functions that are going to be better named and that will show these dependencies. So these dependencies are kind of hidden right here. I like to put arrows in them, right? Your text editor doesn't put these arrows in, were it only so. But we can do better than this by doing something like this. Our whole job here is to get out a certain array, revenue fraction per city. And instead of doing this longhand in this sort of way, where we have to trace the dependencies, what we can write is simply revenue fraction for city equals normalized sum array of some array revenue for city. This is one of the inputs this thing used. The count of the cities and a total up of this array. Okay, that's what's basically going on here. So in other words, the whole job of this code is summarized in this single line once you take into account these methods here. Normalize array, all it does is divide an array, takes an array in, and it divides it by a certain value, the count of the cities here, and then it returns a value. Here we are, excuse me, I stand corrected. This count of cities is the number of cities. This is the length of the array. This is the number by which it divides, array total. So normalized array, its job in life is to essentially do this loop where the value for total revenue is just the total of this array. Okay? And count of cities is used to determine the number of elements, and array revenue for city is the array to be normalized. Total revenue here that we had could be expressed as array total of this revenue per city. Revenue fraction per city can be displayed is that expression. Okay, so this might be an even easier way to write it, where we explicitly we are stating here array total is total revenue. We give it a nice name, and then we use it as the final argument. So either of these, either this way right here under better, or this way right here, are better ways than writing it than this. Do you see that? Do you see why it simplifies things? Because the dependencies are clear. In other words, what revenue fraction per city depends on is three things. It depends on array revenue per city, the count of cities, and then this array total of this array. Array total, of course, has mechanisms in it. It has a for loop, but you don't have to see that unless you want to. You don't have to dive down into this unless you really want to see what's there. Does that make sense? Okay, so another way to write this that, you know, arguably is even better is you give a name to the array total, array revenue, you call it total revenue, and then you use that named concept. So either of these is better than the top one in terms of clarity, in terms of what's going on, what depends on what. So in short, functional abstraction gives us not only generality in the form of parameters, in the form, as we'll see, of abstraction by specification. It not only breaks the code up into pieces different people can work on and that can be tested and debugged and all those good things, but it also makes dependencies clearer. Why? Because we see exactly what something needs to do its job. Array total needs a value passed to it. We know what it returns back. And similarly, normalized array, it's very clear what it depends on. This top code, you have to kind of study it to see what depends on what, what's being computed from what. You know, does this bottom loop depend on the top loop, or are they two independent things? It's not immediately clear. Does that make sense? So here, when we have a use of functional abstraction, these dependencies are much clearer. Okay, I don't want to belabor this point, but you know, here dependencies are clear. You don't have to look at the code for like normalized array or for array total unless you actually want to. It's to a degree self-documenting, and you know, many places in the code can reuse this, right? The function. A function can change without without changing the code that depends on that. We're going to be coming to that. So you know, here's our other example, and we can rewrite it like this: one line with the right functions. This is a crufty piece of code. You can figure it out eventually, but it takes some study. But we can replace it with a single line. That's really, this is what this is doing. It's just now we've given ourselves helper functions in the form of magnitude. We allow us to compute the magnitude of something, which sort of combines this second loop here with the square root. And similarly, dot product, we've carved that out into a function with functional abstraction. Instead of hard coding it for x and y, we just give it parameters here. You see that? We've used abstraction by parameterization to carve out. We've gone from hard-coded values x and y to a function where we simply pass x and y. Yeah? And that allows us to write this logic in a far more transparent way. You get that? And you don't have to figure out what depends on what here. It's totally clear what depends on what. This call to normalize array depends on three things. Depends on x, count dims, and this quotient. This thing divided by that thing. It's clear what magnitude depends on. It's clear what dot product depends on. In short, what depends on what is totally clear. Now, this helps us a lot as software engineers. I couldn't tell you how much more favorable it is to work with code like this than the top code. If it's 11 p.m. at night and I have a customer who needs product tomorrow and I'm worried that I'm not going to get this done because I'm stuck in debugging. If I can be working with this, it's just so much easier. But not only that, ladies and gentlemen, it turns out, and this is one of the reasons, you know, you may think Haskell is just an interesting language to learn principles of languages. Actually, languages like Haskell, languages like Scala, which incorporate functional principles, it turns out are a lot easier to achieve performance speed up of a certain sort. Can anyone tell me here? I mean, many of you are fourth year students, some of you are grad students. There's a certain type of speed up that we can achieve that's becoming more and more important in programming these days. And it depends critically on being able to determine dependencies. Being able to determine what depends on what. And languages that make that clear, like use functional abstraction like this bottom code segment, if languages support that clearly, they can be sped up dramatically compared to languages where it's not clear. Like languages such as C, where you can have pointers to pointers, and it's not clear what modifies what depends on what. What is this type of speed up that I'm referring to?
Parallelization.
Parallelization. Parallelization, where it's at for parallelization, the thing that gets in the way of parallelization is dependencies. What depends on what? Why is that? Because if A depends on B, you can't do what?
Parallelize.
You can't parallel. You can't do them in parallel. You have to do B before A, right? A depends on B. And in languages like C, these dependencies are not so clear. Now, when I was talking with you about C back in 214, or when you learned C in the fullness of your first year, we didn't talk to you about the dark side of C. We didn't talk with you about obfuscated C contests, probably. Does anyone see those? Yeah, okay. Okay, now that's a scary sight to behold. It's pretty funny, but it's not so funny if you're trying to debug the code. The fact is that in C, you can cast what's really a pointer to a large structure and treat it as if it's a pointer to a character. You can treat it as if it's a pointer to a double. And you can write to it accordingly. You can take a union, and something that's secretly an int, you can treat as if it's a char double star. Now, you probably don't want to do this. But in certain operating systems, they'll take advantage of this flexibility to get around needless compiler warnings, etc. So you can read characters in from disk in a file, and you can put them into memory as if they're ints, pieces of ints, and no one's the wiser. And basically, you've been able to persist the state and read the state in of the state of a program or what have you. So it's not to say it doesn't have benefits, but one of the things it gets in the way of is parallelization. Because if you can do all that, if you could take a pointer to this and treat it as if it's a pointer to that, it's really hard to tell what depends on what, really. The code could be doing funky things, and bad things could result accordingly. And there's famous cases of this. Bill Gates, who you folks know predominantly as a billionaire with great philanthropic contributions. Back when he was a hacker, I knew the people who worked with him as a hacker. I had the pleasure of meeting him a number of times, getting invited to his house, and he was famous for what were known as Lixie tricks. Basically, they would use instruction punning. They would overlap instructions by recognizing that these instructions for the processor were encoded in ways that had common bytes. Depending where you jumped in, it would be the certain code, the certain set of bytes would be interpreted as one instruction or another. You jump in a little bit later, it would be interpreted as one instruction. A little bit earlier, a few bytes earlier, it would be interpreted as another instruction. And another thing they do is they use data structures that were meant for data, like tables of cosines, as instructions. Is it data or is it instructions as well? It's both. Sometimes it functions as one, sometimes as another. And they do it in C, in assembly language. That is not amenable to easy analysis by a compiler. And we need analysis by compilers to parallelize things. What depends on what is not so clear. So languages like C, they're close to the metal. They're close to the processor's need to turn it into instructions, but they really inhibit parallelization. Make it very difficult to parallelize code because the dependencies are not clear. I've traced them out here, and this code is pretty easy to trace dependencies. But if you had pointers and some of those things that are being pointed to get written over as part of an array computation elsewhere, it's not so clear what depends on what. Languages that make it clear what depends on what, like functional languages, can be parallelized vastly easier. And in the end, that may provide a much bigger speed up in your lifetimes. than programming things close to the metal. It's that ability to parallelize. It's that ability to have intelligent algorithms of parallelization that may get you much further than writing things close to the metal for certain types of needs. Some of you may have heard, some of you are in 371. Many years ago, when I was a young man, about your age, a little bit older, I was invited to join a small startup based in Cambridge, Massachusetts. Several of my other colleagues in the department, several of my other student friends, they had gone off and formed a company that had ambitious goals. And they knew I was a hacker and could write lots of code. So they invited me to join, and they knew I knew algorithms really well and data structures and very familiar with a variety of languages. And they offered to pay me well and to join the company. And I thought about it a lot, and I decided, I don't think I'll do it. The company was Orbitz. Does anyone know Orbitz? It's for airline reservations. It may be the most popular site for airline reservations worldwide. And they were going head to head with large airline companies at the time. And they succeeded. And one of the big ways they succeeded was by mixing together the right set of languages. So their core code, the code for the most important algorithms, is actually written in Lisp, which is a language not too unlike Haskell in the sense it's a functional language. Now, that doesn't mean the whole system is written in Lisp. There's parts of it written in C++ that need to have somewhat higher performance for very regular routine things. And there's other parts of it, I think, written in Java for certain other components. In short, ladies and gentlemen, you want to pick your languages easily, and you want to get away from this notion that because a language is closer to the metal, it's going to be faster for you. For some things it may be. For other things, parallelization is going to be where it's at. That's how you're going to get your industry advantage. It's by parallelizing. That's how you're going to get your big speed up. Or you want flexible algorithms that are going to be very clever, much more clever than algorithms of other airline reservation sites out there. Needless to say, the folks who invited me have done very well. Very, very well. I think they're long retired. Okay, so in short, ladies and gentlemen, abstracting with functions can really simplify dependencies. I didn't emphasize this last time, but it really simplifies dependencies. We can make it very clear what depends on what. I've gone through this quickly because I want to get to some other very important material in abstraction by specification. But if you're not sure about this, go back and look at this code, and you will find that what's going on in this code is crisply and clearly summarized here at the bottom with this code in a functional style. Functional because we have functions used, and the arguments for one function depend on the results from another function and some expressions evaluating the results. Do you believe that? Do you believe this is the same as that? If you're not sure, go back and look at the code at this slides, okay? Okay, so ladies and gentlemen, we're going to now move on to this issue. And again, okay, come on. I run Linux and I run a virtual machine within Linux for my presentations here. So let me just get to, okay, this is what we want, right? Okay. So we talked about this, and we talked about last time abstraction by parameterization. Okay, so let's go back actually for a second and go look at these motivations for abstraction in the form of what we mean by abstraction. Okay. So abstraction is the process, I say, of putting aside, in other words, abstracting over certain details, in order to treat many particular circumstances as the same. Okay? And that's what we did with parameterization, right? We had this code where B was used for the current state, and then A was the next state, and A was updated, and vice versa. And we used a single piece of code with just passing those as parameters. Or we had run scenario that previously was hard-coded for 100,000 iterations, and we made it a parameter of that function. So abstraction by parameterization is one way we achieve this generalization of many particular instances. We add parameters, and as I said, we're going to see it for many particular cases. But the other way is abstraction by specification. Okay? So let's talk about abstraction by specification. What this involves is something you don't see in that code right now, which is the separation, ladies and gentlemen, of the interface from the implementation. What do I mean by that? Some of you have heard me make that utterance in front of you before. And I suppose it's possible you didn't understand then, but I think I was able to convey it. And you should have seen this in many, many classes by now. Separating interfaces from implementation. What do I mean by that?
An example would be like model view controller.
Okay.
Just how like the part where it like displays on the screen shows you what's happening is a separate module from everything that does the actual processing and bringing things out. Okay,
so I like some of the way that Royce is describing it. So you have a separation between kind of the rendering or the representation and what's really going on under the surface to make that happen. That's part of it. That's part of it in the sense that we're going to separate the what from the how. What this does is going to be separate from how. Can anyone else expand on this separation of interface from implementation when it comes to something like a class, or when it comes to something like an interface in Java, or when it comes to something like a function? What do I mean by I want to separate the interface from the implementation?
Well, it's the idea that like when you're doing functional abstraction, the programmer should be able to call the function expecting that it will do what it does, and they don't have to worry about how it's implemented.
Exactly. Exactly. So they should be able to have some sense of what it does and to be able to count on some contract that they don't have to know all the details. Now this is an example we'll come back to many times during the semester, but it's a little bit about like how you deal, well, often our computational structures end up mirroring structures we've invented over centuries in human context. So when you make a contract, let's suppose that you want to rent a U-Haul truck, or suppose that you want to catch a cab, or suppose that you want to, use Uber to get a ride, or suppose that you want to send a package via FedEx, right? There's a contract involved, and sometimes you read that contract more closely, sometimes you read it less closely, but they basically agree to provide a certain service in return for something on your part. With Uber, you'll be standing in a certain place and you'll pay a certain amount of money, right? There's a contract there that is going to, with FedEx, maybe, if you bring the package in by 10 a.m., they'll guarantee getting it to Ottawa by 5 p.m. the next day, right? Now, very key part of this is that contract specifies certain terms that are guaranteed. If you make the conditions possible, if you adhere to what you have to do on your side, they will deliver certain results, right? And it abstracts away from exactly how. I mean, they could use they could ship your package to Ottawa on the Concorde, right? They could send it on this plane, which is no longer in use, but maybe they bought it. FedEx has bought it. And they're going to ship your package on Concorde, or they could drive it to Ottawa on the Blue Flame, a really fast car that drives across the country. I wouldn't want to be on that car as it winds through cottage country and the Canadian Shield, but they could be driving it that way. They may fly it on a Cessna that the owner of the FedEx franchise owns. You don't care as long as it's guaranteed to be in Ottawa the next day at 5 p.m. Does that make sense? They have a contract with you. You shouldn't have to care about all the details. Does it go out on the 5 p.m. flight or the 7 p.m. flight to Toronto? Or does it go through Winnipeg? That's immaterial to you. You just want this service performed, right? And there's many cases in life where that's what we want. We sign up for service. We don't have to know. We don't want to know all the details because it's unnecessary clutter in our life, right? Unnecessary clutter in our life. Okay. So the details being hidden here, the differences between implementations. In a computational construct, by separation of interface from implementation, we're going to be separating out which particular implementation of run scenario we're going to be using, or particular implementation of update cell. As long as it does its job, we don't care as users of it. And it's just like Eric said, we want to be able to use this code without depending on the vagaries of how it's implemented. We want to know if we provide these parameters. We set it up in this way. We provided a non-null value for its first argument that points to some string, and we pass it two non-negative integers to the next two arguments. They will return for us a string that's a subset of that first argument between position x and y. Yeah? Where position 0 is considered the first position, etc. Okay, so here someone else, the implementer of that method, might substitute in a new implementation of it that's faster. But we don't care. As long as it does the job, our code is not modified because we're still adhering to the contract. If they want to change how exactly, if they want to buy a Concorde to fly it across Canada, they want to buy a Concorde to fly your package, that's up to them. As long as it's there by 5 p.m., you shouldn't really care, right? As long as you're not living the flight path. Okay, what's that? Okay. Okay, so the implementations can be different, but they make use of the same interface. Okay. So why do we do this? Why do we do this? Well, we want to build one piece without worrying about the others, about modifying the others, right? We want to be able to change one piece without breaking other code. That way lies madness, was the quote from King Lear I used last time. If everything depends on everything else. In the sense you change one thing, you have to update everywhere else in the program. And tools like MonoView Controller can help you limit how much changes in one place lead to modifications, require modifications elsewhere. Okay? So here, we're going to reuse opportunities. So let's go talk about how we're going to do this. And again, we're buffering ourselves from change. Okay, so the key question is, how do we define the interface? And what I gave you last time, what I posted on the site, is really impoverished in this regard. It made use of abstraction by parameterization, but we hadn't really made use of abstraction by specification yet. All it has right now, as Royce observed, is precious little comments, but most importantly, there's not comments even on what's the job, what's the contract associated with each piece of that code, right? There's no promise being made about what run scenario does. No statement even runs Conway's Game of Life. I mean, maybe it, simulates a game of checkers on the grid. It doesn't even promise that. And look, I said names are better. Yeah, names are really important, extremely important. They're one of the most important things you can do. But between those and the type signature, what it takes in as arguments and what it returns, those are important things, but they're grossly insufficient for telling us what it actually does. Does that make sense? I mean, if we go and we look at that code, it's not at all clear what it does. It's not clear what job it performs. We could kind of try to deduce it from the names and so on, but we're skating on thin ice here, right? So, we want some way of knowing what does this thing do? What can we count on? This is really most important, ladies and gentlemen. What can we count on? Why? Because that's what allows us to know, okay, we don't have to worry if the code from the other person is modified. It gives the other person clarity on what they can change and what they can't change. What am I counting on? What am I not in using this code? In short, we're seeking a formal contract, okay? Where both sides say, okay, what's the deal? You provide me what, and I provide what in return, okay? And we do this through specification, okay? Okay, so let's go talk about this. Right, so the contract defines the implementation between implementation and reuse. And there are several types of contracts that you'll find out there. We're going to be focusing on certain types of semantic contracts here, and to some degree type-based contracts. There's other contracts. You'll find those who are really interested in the web space will find quality of service contracts or performance contracts in other contexts which are associated with real-time systems. In other words, the system within 10 microseconds will achieve this, this result as a result of this interrupt or what have you. So contracts are all around us, and they are described by specifications. Okay? So why are these favorable? Well, they provide both user of the abstraction, the creator of that function, guarantees on what things can be modified, and users of the abstraction can have clarity on what things they can count going forward. Even if a new library version comes in, they can count on certain things being the case. Okay. And it's going to help conceptual clarity, earlier opportunities for review of detailed design. Why do I say that? Particularly those who have taken, there's just a couple people who have taken 371. Why do I say that it can help, to have specifications can help earlier review, earlier peer review, inspections, for example? Why can it help?
Because it shows that you know what's going on mentally?
That's right. It gives you a very clear understanding of okay, what are the pieces, so you have an entire functionality you're trying to achieve, what are the contracts that are required, needed to achieve that, and often all you have to do is specify a few other things, like this will depend on this and this, and you can see the degree to which they're compatible, at least at a high level. You can spot a lot of inconsistencies, for example. More than that, there may be code, a large portion of code that's not yet written or operational, but other code that is written and operational can be examined as to whether it's going to work with this other code, because you have these contracts in place, right? Now, I talk about direct derivation of many assertion checks. How many people in here have used assertions before? Okay, good. So you should know what do I mean by this?
This has to be true or something is very wrong.
Yeah. If you have a contract, it's really obvious things that need to be the case. That's actually not a list of all things. There may be certain implementation details that you additionally want to check. But it gives you, for free almost, a lot of things that you can check as part of your code. Test case creation, I think it's pretty clear, right? If you have contracts, you know if I give it these things, it should always return this. And it should always return a value within this range, or a non-null value, or reference to a file that's writable, or what have you. And it's really easy to write test cases against these things, right? Easier integration, understanding of code, etc. And in short, it's a bit of a pain, perhaps, to write, but it can often spare you a lot of time. Okay? So it speeds up debugging, testing, development, and it also can help performance by making it very clear what optimizations are clear and what are not. Okay. I provide some examples here. Without contracts, it's really hard to tell. For example, can the order of these things be changed? If I have 2 calls to this, can I just replace it by 1 call and just reuse the value, for example? It's not clear, because if P is performing a what, like this is not the same. If P is performing a, begins with S, 2 words, side effect. If it's performing a side effect, right? If P is sending out a message every time I call it, right? Or posting new data to a database, calling it twice is going to not be the same as calling it once. On the other hand, if it's functional, if it's a pure function, if it has no side effects, you call it once, and you can just reuse the value, right? You know, there's a global variable, and I get that value. Then I call p, and then later I reuse the result of that global variable. Is that the same as, or do I have to, after calling p, do I have to get the global then because p changed the global variable? In short, there's a lot of cases where if you don't have a contract, you know, lots of things could happen, and you're not sure what can what's safe. So in short, if we want to tame the dragon of side effects, if we want to have modularity in our program, having abstraction by specification is key. Having this these components. So let's talk about this. So the specification needs to balance in its level of detail. Detailed enough information we can count on key functionality, but it needs to rule out certain implementations that don't meet the needs. Okay. So the user needs to know what's guaranteed, and have enough clarity on that they know, okay, you know, this is going to be able to handle cases in the way that I expect. But it needs to be general enough that the user can have confidence that the person who provides the abstraction can have confidence that they can change the implementation, certain aspects of the implementation. Okay, some of you have seen these before in 371, but you know, if we have an index string, for example, we might provide a statement of the effects here in English and give some examples of this, right? And I'm going to ask you for this code and then for modifications of this code that we're going to be introducing to put in place some of these contracts of sorts. You should have done it in other cases, but we're going to want to see how those change over different programming languages, and we're going to talk about how they affect the modularity of the program. Okay, now there are things you have to watch out for. Ambiguity is one of them. We're never going to have a perfect description. The goal is to have a description that's small enough, crisp enough, it's likely to be read and really thought about, but it's not so ambiguous. So what's ambiguous about this one here? Subset. If S1 or S2 is null, it throws this, otherwise returns true. If S1 is a subset of S2, otherwise returns false. What's ambiguous? What's not so clear?
S1 and S2.
Okay, S1 and S2, these are the two arguments here. And it's very common that this specification would refer to the names of the arguments, because after all, these are what has to be provided for it to do its job, right? Is these things. So those are provided as part of the preconditions. These need to be provided, and you know, it says here, if they're null, it will reject it. Essentially, will throw a null pointer exception. So by implication, these things should be non-null. Okay, and that could be improved some. But what else is ambiguous here? Just at a logical level of set theory.
What if the two are equal?
Yeah, exactly. It doesn't really resolve. Okay, when it's saying it returns true if S1 is a subset, does it mean proper subset? In other words, it's strictly a subset, or if they're equal, should it also return true? It's not so clear. Here, by contrast, it could be more detailed. Returns true if every element of S1 is an element of S2, otherwise returns false. This resolves that issue because it makes it clear if they're equal that it will return true or false, the second way. If they're equal, it will return S1 is the same set as S2, will the second one return true or false? According to this, does it make it clear it returns true or false? True, indeed. Here, one can also have, this more detailed one as a disambiguator for the first. The goal here is not perfection. The goal is to communicate enough that it's pretty clear what can be counted on, and it's small enough to be easily readable, right? Okay. Too cold. Returns true if temp is less than or equal to 0 degrees Fahrenheit. Otherwise, returns false. Okay. It's better than this, or even better version of this. Returns true if temp is less than or equal to 0. Otherwise, returns false. I.e., returns true exactly when temp is not greater than the freezing point of water at standard temperature or pressure. Why is this helpful? What does it show? What does it show that needs to be corrected?
Is it the freezing point of water 32 Fahrenheit?
Yeah, exactly. It's not 0. It's not 0. So here, perhaps this was written when a person was really tired. They didn't quite get it right, and it remained hidden. Here, it's clear that there's an inconsistency between the value given, 0, or the units, Fahrenheit. Maybe they meant Celsius, or centigrade, or maybe, in any case, it's not consistent with this claim that it's related to the freezing point of water. Billion. What's the matter with the term billion? Turns the integer 1 billion. Turns out that billion means something different in England. I think it's 10 to the 12th or something like that. In any case, in North America it's used 10 to the 9th. In another place it's used 10 to the 10th. And so putting in a little bit of information to be very clear, to be, go beyond just mirroring the name and making it clear what the value is, that can be useful. Okay, now I want to distinguish. This is important for you doing this next little exercise. I want to distinguish between two types of specifications. One are declarative and definitional specifications, and the others give a high-level description of how. And I strongly encourage the first of these things. Well, when I say first, that's ambiguous, isn't it? The bottom one, what? Okay. So the top one here, this is search. So we pass in an array and a value for which to search, and it says, pay is null, it throws this exception. Otherwise, it examines A0, A1, A2, etc. in turn and returns the index to the first that is equal to X. And it signals not found exception if none equals X. And let's compare that with the bottom one. Here, it says, it's going to throw a null pointer exception. Great. But otherwise, it just returns the I such that A of I equals X. And it throws this other exception if there's no such I. Why is this bottom one more favorable? If you were writing this code, the code for this, if you were providing an implementation of search, why would it be more favorable to have the bottom one rather than the top one?
We don't care how it does it, we just care what it does.
Exactly. But why? What's the benefit of that? At a practical level, if you were providing a library that provides this, what is it about the bottom that gives you serious benefits?
You could change how it does the search without having to counting on something being there.
Exactly. So it gives you more flexibility, right? This top one, it kind of gives away more than it needs to. It leaves money on the table. It promises a certain level of behavior that is more detailed than necessary. Now, why do I say it's more detailed than necessary? Necessary for what? For whom?
For whoever needs to call that function.
Whoever needs to call that function. Do you think do you think that they are likely to depend on the exact order that it searches? A0, A1, A2? Probably not so much. And therefore, why promise it? Now, could you imagine something that makes clear, that's made clear in the first, that's left unspecified in the second? this first of them, what is pinned down here that's left up in the air here? There is a piece of information here that might be practical, might be useful for someone to know.
The operation one specifies that it's the first one.
It's the first. It's the first. This one doesn't specify that. Could this specify it, but still remain fairly general?
Yeah.
It could. Is it okay that it doesn't specify that? Is it okay? Yes, it is. It is. I mean, look, there's nothing that requires a contract to be exhaustive. So this leaves it up in the air. If there's multiple I's, such that this is the case, then basically you're not sure which I it's going to return. Now, for most people who's going to use this, it probably won't be a problem. If it is a problem, you say, look, I want to know which, if there's multiple of them, I always want to get the first. Maybe you're not going to use this function, right? Because you're not sure it's guaranteed. On the other hand, if you guarantee the first, what's the trade-off there? What disadvantage is there if this were expanded to say it always returns, if there's multiple of them, it always returns the first? What's the disadvantage if you're the creator of this?
Then, regardless of the implementation, you always have to make sure it does return the first one.
Exactly. So maybe you want to implement this with a binary search or something, and now you're a little bit, your hands are a little bit tied, because you might be able to actually have a quicker algorithm when there's, that if you don't have to guarantee this. But the fact that you do have to guarantee it means you have to put in some additional checks or what have you. And it slows down the average case, at least a little bit. So in short, what you promise and what you don't promise, it's a pragmatic matter of knowing what flexibility do I want. What level of promise do I want to make is a strategic decision that you can make. If you don't want to pin something down because you want to give flexibility to handle certain cases, you can choose to do that. What it may mean, worst case, is that a person may not use your component because they say it doesn't provide me the promise that I need. On the other hand, it may provide you the opportunity to evolve it in other ways. Is that clear? So specifications. Let's pop up to a high level. We were talking the first part of this class about functional abstraction. Abstraction by parameterization was part of that. Now we're talking about abstraction by specification. Do you see? This is a very important point. Forgive me because we're trying to deal with some basics in this course before we get to some more advanced material. Is it clear, ladies and gentlemen, why when I say we have abstraction by parameterization, that providing a specification that promises some things and not others, that it allows us to basically deal with many possible implementations of this using the same set of promises. That we can make the same set of promises here, and there's hundreds of potential implementations, maybe thousands, right? You could use a heap. You could use a sorted list. You could maintain a hash table with this, and any number of different things that are going to implement this. And that's up to you. And the user doesn't have to care if you switch from one to the other, right? And the point is, the fact that we're giving specifications allow us to handle many particular cases of a function implementation, allow us to handle any number of those with the same basic specification. So the fact that we provided this specification allows the user of this construct of search to avoid counting on features that may evolve. And therefore it allows their code to work perfectly happily as you evolve your site. This captures many particular implementations and therefore allows you to substitute in new ones. Does that make sense? Okay, that's abstraction by specification at a function level. And we're going to see this in a little bit at a class level, type level, with the Liskov substitution principle. Okay. So declarative specifications are generally easier to understand. They admit greater flexibility and greater potential for automated reasoning. Now, in your professional lifetimes, and in mine, you are going to see increasing use of what are known as formal specifications. Okay, and these things go beyond what we've just seen. They get the benefit of what we've just seen, but they provide extra benefits. They go beyond this. This is written in English. And it's not a matter of perfection. It's a matter of communication to others whose command of English is pretty good. And it provides a lot of benefits. But the specifications there, they're informal. They're in comments. They're longhand documentation. They're vastly better than not having them. But they can't be understood directly by a compiler. You get that? Why not? Why can't the compiler understand those things and reason about them? Say, you made a mistake. You're not adhering to this. Why not? Well, as an old compiler writer, I'll tell you, our compilers are, if you could take a compiler course, it's really worthwhile. But compilers have an amazing ability to deal with the complexity of software development involved. It's very impressive. Nice combination of language issues, language hierarchies, and software engineering. Beautiful stuff, machine architectures, etc. But they don't include natural language reasoning and so on. And they need to understand English and the subtleties of English, etc. We're not yet at that point. So instead, what we do is we create specification languages. And I'll show you some in just a moment. But there's benefits here for more aggressive optimization. If you can specify it formally in a logical form, so it understands what you mean logically, you can actually do much more aggressive optimization. You can find problems. Now, did any of you take 340 when it was taught by Professor Duchin? No? Okay. And he talked about the language COQ, C-O-Q. Did any of you see that? Oh. Any of you heard about this language? Yeah. Well, what have you heard about it?
Has a funny name.
Okay. Fair enough. What else?
Everything is mathematically proven.
Okay, good. Yeah, and they've actually done verification of whole operating systems and compilers with this language. That's really significant, ladies and gentlemen. It means that you can have a compiler that's not only got lots of eyeballs on its code and it's been really tested on lots of programs and it seems to work, but it works. Logically, it has been proven that the algorithms involved are correct, that it will produce the correct code under the right circumstances. Compilers are very complex, and to be able to have achieved that is remarkable. Same thing for an operating system. No more blue screens of death. It's going to work. For these situations, the context switching machinery associated with processes is going to be operating correctly. And at a more prosaic level, you're going to be writing code increasingly which can take advantage of these formal specifications. It can find errors in your code, identification of inconsistencies. It can help prioritize test requests and code review requests. Now, these are some of the specification languages out there, and this happens to be an area where things are advancing very rapidly. Eiffel, which used to be taught in our department, has the components Z and Z++. Alloy is a big project at MIT that's achieved a lot of interest. I've contributed to the Splint project in the past, which works with C and specifications in C, and you'll find Spec Sharp for C Sharp out there. These are not pie in the sky stuff. This is stuff which is starting to really make the difference in code quality in certain areas. These are examples of formal languages. Here's Spec Sharp, right? Here's ABS, and it ensures 0 is less than or equal to x. If this is the case, the result is x. If x is less than 0, the result is minus x, and then this is the implementation of it. This is a specification here, and this is something which basically summarizes what this accomplishes. It's decidedly a small function here, but this can be used at a much larger level, particularly when the code is broken up into nice pieces. Okay, time is up for today, but I'm going to ask you, and I'm going to be posting this, and I try to do it for these homeworks over the weekend if possible. I'm going to be posting a little task for you to try to apply some of these preconditions and postconditions here to that code for preconditions and postconditions. And then we're going to examine how does that code evolve in an object-oriented context in coming lectures with the Liskov substitution principle, then starting to introduce additional richness to our reasoning about specifications, okay? But this issue of specifications in formal specifications we'll be revisiting over time as we come to additional types of languages. And we'll take a little bit of a look at these formal languages for specification. Okay? So that's all for today. I'll be posting this lecture, and I'll be posting the homework. Also, I think there's a turn in there for those interested in pursuing projects. I'm asking for a brief blurb about your project soon to be posted there. I think it's due this week, if memory serves me. You can check the dates if you want to talk with me about it as normal life office hours for the next hour. Okay? So that's all for today. Thanks. Oh, and enjoy the career fair. Remember, the career fair is today. If you haven't gotten a chance to get there, I encourage you to do so. Okay?